Okay, section 3.4 in the textbook is elemental analysis. To find the percentages of carbon, hydrogen, and oxygen in an unknown compound. This is a real analysis done when you have either plant material, want to know what the carbon-nitrogen ratio is, or if you make a new compound in organic chemistry and don't know what the formula is for it. This is a real analysis that is done. Okay, and so we're just going to deal with hydrocarbons, which means a carbon that's only carbon and hydrogen. And it's burned, which means that we introduce oxygen, and it always produces carbon dioxide and water. So this right here is the generic equation that I have. This is my hydrocarbon with only carbon and hydrogen, and you notice I have subscripts of X and Y and oxygen. Okay, so this is a picture of the setup, and oxygen is being taken in from the inside. So even if this compound has oxygen there, I also am supplying oxygen. Okay. So the X here goes to the X there, okay? So that's the coefficient. So that means that for every mole of carbon, 1 mole of carbon dioxide is produced, okay? So that's what the X and the X, they're the same number there. For the hydrogen, I have the subscript Y, but over water, I have Y divided by 2. And why is that? Because every hydrogen that I have in my molecule, I only produce half of the waters because of the fact that each water has 2 hydrogens. So it's 1/2 of the moles of water that's formed. So as I said, this is the experimental setup. Okay, so I take my organic molecule, my hydrocarbon, and I put it into a dish inside of a furnace so I can make it very, very hot. I blow in oxygen, pure oxygen, and I have basically, this is just a stop to keep any of the solids from going through, okay, copper oxide. It also helps make sure that everything's converted to carbon dioxide. This is like a catalytic converter. So the first place is TRAPSIA water. Okay, this is a material that likes water a lot, so water sticks to it, and so it basically can increase the mass of water here. And then it bubbles through a solution of carbon dioxide, and carbon dioxide and sodium hydroxide react, and so I measure how much sodium hydroxide has been reacted, and from that get the carbon dioxide. And then any excess oxygen just bubbles out. I could have added the tubes if I want to collect the nitrogen and that type of thing, but that's not shown in this display. So, an example of this is problem 64 from chapter 3. Phenol is a commonly known carbolic acid, okay, used by Joseph Lister as an antiseptic for surgery in 1865. It was the first antiseptic used. Today it's used for phenolic resins and plastics. Now, I changed all these. In the book, it has milligrams. I just changed to milligrams. It doesn't matter. So I have 5.23 grams of my phenol, so of my sample, yields, okay, 14.57 grams of carbon dioxide and 3.01 grams of oxygen. And phenol contains carbon, hydrogen, and oxygen, and it wants to know what the mass percent of the substance is. Okay, so as usual, the process is to take the numbers and write them down. So I have 5.23 grams, and that's of the phenol, or of the sample. I have 14.57 grams of carbon dioxide, and I have 3.01 grams of water. In order to do this problem, I also need the molar masses. So I need the molar mass of carbon dioxide, which is 44.01, the molar mass of water, which is 18.02, the molar mass of carbon, which is 12.01, and the molar mass of hydrogen, which is 1.01. So I'm going to do carbon first, okay? So I'm going to start out with the mass of carbon dioxide, okay? And in order to compare amounts, I have to be in moles. So what we did in section number 2 of this chapter was found how to take mass and go to moles, which is you take the mass divided by its molar mass, and that gets you moles. So I have 14.57 divided by 44.01. The grams cancel, leaving me moles. Now I need to go between carbon dioxide and carbon. In the last slide, we said that for every 1 mole of carbon dioxide, I have 1 mole of carbon. So it's a 1-to-1 ratio, but you need to show that. That's part of the partial credit for showing your work. And then I need to find the mass of carbon, so I need to multiply. So I'm going from moles of carbon to mass of carbon by multiplying by the molar mass of carbon, which is 12.01. And so I get 3.976 grams of carbon. Okay. To find the percent carbon, I take that mass of carbon divided by the mass of the total phenol times 100, and that gives me 76.0% of carbon. Now, the next one is I'm going to find hydrogen, and from hydrogen, I'm going to start from the water. So I have 3.01 grams of water. Again, to compare amounts, I have to be in moles. So to go from grams to moles, I divide by the molar mass. I'm going to divide by the molar mass of water of 18.02. Okay, this time it's not 1-to-1. If I look at this water, how many hydrogens do I have inside this water? Okay, so there's 2 moles of hydrogen. There's 2 right here for every 1 mole. So I have 2 hydrogen atoms for every 1 water molecule. Okay, so I have to multiply by 2. And then times the molar mass of the hydrogen, which is 1.01, and I get 0.3374 grams of hydrogen. Again, I take that mass divided by the mass of the phenol times 100, and I get 6.45%. Now, I can't get oxygen the same way. The reason is, as you see, I have oxygen here, I have oxygen there, so I can't start from both of those because they're different compounds. Plus, as you saw in the diagram, I pumped in oxygen, so oxygen comes in freely. So I always get oxygen by percent difference. So the percentages that we showed in the last section, they have to add up to be 100. So I take 100 minus the 76, so this is the carbon. So this is the carbon, and this is the hydrogen. Okay, so 100 minus the carbon minus the hydrogen gives me 17.5% of the oxygen. Okay, and so that I always have to do oxygen by percent difference. If the problem only gives the carbon dioxide, then that means the original compound does not contain oxygen, only has carbon and hydrogen. So just like we did with the previous problem with oxygen, I can get the percent hydrogen from subtracting the percent carbon from 100. And that is the end of this section.